If you were to sort the worlds of the solar system by how much liquid water they hold, Earth would not come first. It would not come second either. We are the water planet. That is how we describe ourselves, and it is not wrong. 7/10 of this world's surface is ocean, and every living thing on it depends on that fact. But the ranking, as best we can currently measure it, places Earth somewhere further down a list headed by worlds most people could not name, in a region of the solar system so cold and so distant that nothing there was expected to be liquid at all. The water is out there, it is simply where we could not see it. Begin far from here, past the asteroid belt, out where the sun has become something smaller. At Jupiter's distance, sunlight carries about 4% of the energy that falls on Earth. At Saturn's, roughly 1%. The sun is still the brightest thing in the sky by an enormous margin, bright enough to hurt to look at directly, but it no longer warms anything. It is a source of light without meaningful heat, and the worlds that orbit out there have surface temperatures measured in the low hundreds of degrees below zero. At those temperatures, water is not a substance that flows, it is a construction material. It behaves the way granite behaves here, hard, brittle, load-bearing. Mountains can be built out of it, it fractures rather than melts. And so the moons of the outer solar system present themselves as exactly what you would expect. Pale spheres of ice, scarred by impacts, silent, unchanging, objects rather than places. For most of the history of astronomy, that was the entire assessment, and it seemed sufficient. The assumption underneath it was reasonable, and it went almost unexamined for centuries. Warmth comes from the sun. Move far enough away and things freeze. There is no other significant source of heat available to a small body in deep space, and therefore, past a certain distance, everything is frozen through, surface to core, permanently. That assumption was wrong in a specific and consequential way, and the correction has rearranged our sense of where water exists in the universe. Consider what liquid water actually requires. It requires a temperature above its freezing point, which depends on pressure and on what is dissolved in it. That is essentially the whole list. It does not require sunlight. It does not require an atmosphere. It does not require a magnetic field or a particular chemistry or proximity to a star. Provide enough heat from any source whatsoever, and water is liquid. The question then is whether there are heat sources besides the sun. There are two of them matter here. The first is radioactive decay. Every rocky body contains a small proportion of unstable elements, uranium, thorium, potassium isotopes, inherited from the material the solar system formed out of. As these decay, they release energy as heat continuously for billions of years. This is the process that keeps Earth's interior molten and drives our volcanoes and plate tectonics. It operates in any body with a rocky component, regardless of where that body sits. The second is gravity, and this is the one that transforms the picture. A moon orbiting a giant planet is not simply held in place, it is squeezed. The gravitational pull on the near side of the moon is stronger than on the far side, and that difference stretches it slightly along the line between them. If the orbit were perfectly circular, that stretch would be constant and nothing would happen. The moon would simply hold a slightly elongated shape and stay that way. But orbits are rarely perfectly circular. When a moon swings closer to its planet and then further away, the strength of the stretching changes over the course of each orbit. The moon flexes. It is pulled into a slightly different shape, then relaxes, then is pulled again over and over for as long as the orbit persists. Bending anything repeatedly produces heat. You can demonstrate it with a paper clip, work it back and forth quickly enough, and the bend becomes warm to the touch, because the energy of the deformation is dissipating as friction inside the metal. Now scale that up to an object thousands of kilometers across, flexed by a planet 300 times the mass of Earth, continuously, for 4.5 billion years. The heat generated by that process is not marginal. In the right circumstances, it can be enormous, sufficient to melt the interior of a world that receives almost no light at all. This is called tidal heating, and it is the reason the outer solar system is not the frozen graveyard it appears to be. The consequence is a particular kind of world, and it is worth describing carefully because it is genuinely unlike anything in our ordinary experience. Take a moon made largely of water ice with a rocky core. Heat it from within by radioactive decay in the rock, by tidal flexing throughout the body, or by both. The interior warms. At some depth, the temperature crosses the melting point, and the ice there becomes liquid. But the surface does not melt. The surface is exposed to space, radiating heat away into a void that is a few degrees above absolute zero, and it stays frozen solid. What forms is a shell, a crust of ice, tens or hundreds of kilometers thick, entirely rigid, with liquid water underneath it. The ice floats because ice is less dense than water. So the shell sits on top of the ocean, the way an ice sheet sits on a polar sea, except that it covers the entire world with no shoreline anywhere. And the ocean beneath it is completely sealed. No sunlight reaches it. No atmosphere touches it. It has no surface in any sense we would recognize, no waves, no horizon, no sky. It is bounded above by ice and below, in the best cases, by rock. It is entirely dark at pressures far beyond anything in Earth's oceans, and it may have been that way, uninterrupted, since not long after the solar system formed. These are the hidden oceans, and the reason the phrase carries weight is that liquid water is not merely interesting as a physical curiosity. It is the single environmental factor most closely associated with life. Every organism we have ever found is built around water. It is the solvent in which all terrestrial biochemistry occurs, the medium that lets molecules dissolve, move, and encounter one another. Life on Earth can survive without oxygen, without sunlight, without warmth, at pressures that would crush a submarine, in acid, in brine, in rock. It cannot survive without liquid water, or at least, nothing has ever been found that does. Which is why the phrase, "follow the water," became the organizing principle of astrobiology. When searching for places where life might exist, water is the first filter. For a long time, that search pointed inward. Mars, which plainly had water once and may have some now. Venus, which may have had oceans before its atmosphere ran away. The narrow band around a star where temperatures permit liquid water on a planetary surface. The habitable zone, which is a small ring in an otherwise enormous system. The hidden oceans break that framework because they do not depend on the habitable zone at all. A world with a tidally heated interior can maintain liquid water anywhere. Distance from the star becomes irrelevant. The zone of possible habitability expands from a narrow band into something far larger and stranger, potentially any icy body in any system, orbiting any planet massive enough to flex it. There was a second assumption that needed to fall before this could be taken seriously, and it fell on Earth in 1977 on the seafloor of the Pacific. Until then, it was understood that ecosystems require sunlight. Plants capture it, everything else eats the plants or eats the things that eat them. Energy enters biology through photosynthesis, and without a sun, an ecosystem has no foundation. What was found on that seafloor changed that, but that discovery deserves its own telling, and we will come to it. For now, hold the shape of the idea. There may be more liquid water beyond the frost line of this solar system than on the surface of the planet you're standing on, locked inside small frozen moons, sealed under ice, sitting in permanent darkness, warmed not by any star but by the gravitational grip of the giants they orbit. Some of it has been liquid for 4.5 billion years. And nowhere is the evidence for such an ocean more compelling or more thoroughly examined than on a moon of Jupiter slightly smaller than our own, a world whose surface is so young, so smooth, and so relentlessly fractured that something underneath it must still be moving. Look at Europa from a distance, and the first thing you notice is what is missing. There are no craters. Almost none anyway. Across a sphere 3,100 kilometers across, fewer than 30 impact structures larger than 10 kilometers have been identified. its neighbors are saturated. Callisto's surface is so thoroughly cratered that new impacts have nowhere left to land without erasing an old one. Europa is nearly blank. That single absence is the beginning of everything. Craters accumulate. They are the record of 4.5 billion years of debris falling out of the sky, and nothing in the outer solar system has been spared. A surface with almost none is a surface that has been resurfaced, wiped clean and rebuilt, recently enough that the record has not had time to reassemble. Estimates place Europa's average surface age somewhere between 40 and 90 million years. On a solar system timescale that is not the distant past, it is a rounding error. Something is erasing Europa's face, and on a world where the surface material is water ice at a temperature around 100 degrees above absolute zero, there is a limited menu of things that could be doing it. Europa is the smallest of Jupiter's 4 large moons, slightly smaller than our own, about 90% of the moon's diameter and a little more than half its mass. It orbits at about 670,000 kilometers from Jupiter, completing a circuit in 3.5 days. Like the other large moons, it is tidally locked, keeping one hemisphere permanently turned toward the planet. Its bulk composition is the first clue about its interior. Europa's density is about 3 grams per cubic centimeter, high enough that it must be mostly rock, unlike the more ice-rich moons further out. The picture that emerges is a rocky, possibly iron-cored body roughly the size of our moon, wrapped in an outer layer of water perhaps 100 kilometers thick. 100 kilometers of water. The question is how much of it is frozen. The surface itself is extraordinary to look at. It is among the brightest surfaces in the solar system, reflecting most of the sunlight that reaches it, which is why it appears as a clean white sphere from a distance. Up close, that whiteness is crossed by an intricate tangle of dark lines, thousands of them, running for hundreds and sometimes thousands of kilometers, curving and intersecting across the entire globe. These are the linnae, and they are the most striking feature of the moon. Some are simple cracks, many are double ridges, a pair of parallel raised walls, perhaps 100 meters high, running side by side with a narrow trough between them, extending for enormous distances with remarkable consistency. They are colored. Against the white ice, the linnae appear reddish-brown, and the color is concentrated along the fractures themselves, as though something has welled up through them and stained the ice on either side. Beyond the ridges, other terrain types appear. There are regions called chaos terrain, where the surface looks as though it has been broken into blocks, rotated, shifted, and refrozen in place. Angular plates of ice, clearly once joined, now scattered and tilted at odd angles within a matrix of rougher material. Some blocks have visibly drifted from their original positions, and in several cases the original pattern can be reconstructed by mentally sliding them back together, the way one might reassemble a broken plate. There are also smooth bands, wide stripes of newer material where the crust appears to have pulled apart, and the gap filled in from below, structurally similar to what happens at spreading ridges on Earth's ocean floor. All of this describes a surface that has moved, not once but repeatedly, and in ways that require the ice to be sitting on something that can flow. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003 and made 11 close passes of Europa, gathered most of what we know. Its cameras returned the images that revealed the chaos terrain and the double ridges in detail, but its most decisive contribution came from an instrument that was not looking at the surface at all. The magnetometer. Jupiter has an enormous magnetic field, by far the strongest of any planet in the solar system, extending millions of kilometers into space and rotating with the planet every 10 hours. Europa orbits inside it, and because Jupiter's magnetic axis is tilted relative to its rotation axis, the field Europa experiences is not steady. It sweeps back and forth, changing direction and strength as Jupiter turns. Here the physics becomes useful. When a conductor is placed in a changing magnetic field, electrical currents are induced within it, and those currents generate a magnetic field of their own, one that opposes the change. This is basic electromagnetic induction, the principle behind transformers and metal detectors. Galileo measured a magnetic field around Europa that varied in exactly the way an induced field should, changing in step with Jupiter's rotating field, oriented to oppose it with the right strength and timing. Europa contains a conductor, a large one close to the surface, spherical in shape. Solid ice is a poor conductor, rock is a poor conductor. The material that fits the measurement is a salty liquid, an electrolyte solution in which dissolved ions carry current freely. Seawater conducts well for exactly this reason. The signature implied a conducting layer beginning within perhaps a few tens of kilometers of the surface and thick enough to be substantial. Combined with the surface geology and with gravity measurements from the same flybys constraining how mass is distributed inside the moon, the conclusion has become one of the more secure inferences in planetary science. Europa has an ocean. It is global, wrapping the entire moon with no land anywhere. It is salty, and it is enormous. The numbers depend on how thick the ice shell is, which remains genuinely uncertain. Estimates for the shell range from perhaps 15 kilometers to as much as 30, with a minority of models arguing for less. Whatever the shell thickness, the ocean beneath is likely between 60 and 100 kilometers deep. Earth's average ocean depth is under 4 kilometers, which means that this small moon, smaller than ours, plausibly holds 2 to 3 times more liquid water than every ocean, sea, lake, and river on Earth combined. The question of the ice shell's thickness is not a minor detail, and it is worth understanding why it matters so much. Two competing models have been debated for years. In the thick shell scenario, the ice is tens of kilometers deep and moves primarily by slow convection, solid ice creeping over geological time, the way glacial ice flows. In the thin shell scenario, the ice is much thinner, and the ocean below comes close enough to the surface that liquid can occasionally reach it directly. Everything about Europa's potential habitability depends on the answer, because habitability depends on exchange. An ocean sealed off completely from everything above it is a static system. An ocean connected to the surface is something else entirely. And there is a reason to think the connection exists. Those reddish stains along the fractures have been examined spectroscopically, and the results point to salts, magnesium and sodium compounds, sulfates and chlorides, mixed with sulfur compounds derived from Jupiter's moon Io, whose volcanic output coats much of the Jovian system. In 2019, sodium chloride specifically, ordinary table salt, was identified on Europa's surface, concentrated in geologically young regions. Salt on the surface of an icy moon has to come from somewhere. The straightforward explanation is that it came from below, carried up in liquid that emerged through cracks and froze, leaving its dissolved load behind. The surface, in other words, may be painted with the ocean. That matters enormously for a reason having to do with energy. Jupiter's radiation environment bombards Europa's surface constantly, and that radiation splits water molecules, producing oxygen and hydrogen peroxide in the ice. If surface material cycles downward, carried into the shell by the churning of chaos terrain, or subducted at the bands, then oxidizing compounds could be delivered into the ocean below. An ocean receiving oxidants from above and potentially reduced chemicals from a rocky seafloor below would have a chemical gradient running through it. And chemical gradients are what energy is made of. Whether that is happening is unknown. Whether the seafloor is active is unknown. What is known is that beneath a shell of fractured ice, on a moon slightly smaller than our own, there is a dark, salty ocean twice the volume of Earth's, which has probably been liquid for most of the age of the solar system. Nobody has ever sampled it. The ice stands between us and any direct measurement, and drilling through tens of kilometers of it on another world is beyond anything currently possible. Which is what makes another moon, far smaller and much further out, so remarkable, because on that world the ocean does not stay hidden, it leaves. In 2005, a spacecraft flew past a small moon of Saturn and detected something that should not have been there. The instrument was a magnetometer, and it registered a disturbance in Saturn's magnetic field around the moon, the kind of bending that happens when field lines encounter an obstacle with an atmosphere. But Enceladus is 500 kilometers across. A body that small, that cold, cannot hold an atmosphere. Its gravity is far too weak. Any gas would drift away within a geological instant. The mission team did something unusual in response. They adjusted the flight plan, bringing Cassini in for a much closer pass than originally scheduled, down to 170 kilometers above the surface. What they found there is arguably the single most consequential discovery of the entire Cassini mission. Enceladus is tiny, 504 kilometers in diameter, small enough to fit comfortably within the borders of most large countries, with a surface gravity roughly 1% of Earth's. A person standing there could jump higher than a house and take the better part of a minute to come down. Everything about its size argues that it should be geologically dead. Small bodies lose heat quickly, and a moon this modest ought to have frozen solid within a few 100 million years of its formation. It is also the most reflective object in the solar system. Enceladus returns essentially all the sunlight that strikes it. Its surface is brilliant white, cleaner and brighter than fresh snow, which is part of why its surface temperature is so extraordinarily low. It absorbs almost nothing. That brightness, it turns out, was itself a clue. A surface exposed for billions of years accumulates dust and darkens. Enceladus is spotless, which means something is continuously coating it in fresh ice. The southern hemisphere is where everything happens. Cassini's cameras revealed a region unlike anything on the rest of the moon. A roughly circular area around the South Pole, largely free of craters, cut by 4 long parallel fractures running for about 130 kilometers each, spaced roughly 35 kilometers apart. They were nicknamed the Tiger Stripes, and they are formally named after cities in the Arabian Nights: Baghdad, Cairo, Damascus, Alexandria. An infrared instrument found them to be warm. Not warm in any human sense, the temperatures involved are still catastrophically cold, but dramatically warmer than the surrounding terrain, and warmer than sunlight at Saturn's distance could possibly explain. Heat was escaping from inside the moon, concentrated along those 4 cracks. And material was escaping with it. The plumes are enormous relative to the moon that produces them. More than 100 individual jets have been identified along the Tiger Stripes, and together they eject water vapor and ice particles hundreds of kilometers into space, a substantial fraction of Enceladus's own radius. The total output is on the order of 200 kilograms per second, continuously. Most of that material falls back, coating the moon in the fresh snow that makes it so bright. Some of it escapes entirely, and this solved an unrelated mystery. Saturn's E-ring, a broad, tenuous, diffuse ring far outside the bright main rings, had never been adequately explained because the fine particles composing it should be dispersed within a few thousand years. Enceladus orbits within it, and Enceladus is the source. The ring is the moon's exhaust. Cassini then did something remarkable. It flew directly through the plumes, repeatedly, over a series of encounters, including one pass at just 49 kilometers above the surface in 2015. The spacecraft sampled the material with its onboard instruments. That single capability transformed Enceladus from an interesting moon into the most accessible, potentially habitable environment beyond Earth. Every other candidate requires drilling, melting, or landing. Enceladus delivers its own interior to anything that flies past. What the instruments found, one component at a time, built into an increasingly striking picture. Water vapor dominating the plume composition, around 90%. This established immediately that the source was water, not some other volatile. Salts, the ice grains contain sodium chloride and other sodium and potassium salts at concentrations comparable to seawater. This mattered a great deal because salt does not come from ice. It comes from water that has been in prolonged contact with rock, dissolving minerals from it. The salinity told scientists that the source was liquid and that the liquid was touching a rocky seafloor. Silica nanograins, tiny particles of silicon dioxide, found in Saturn's E ring and traced to Enceladus. The size distribution was the informative part. Grains of that particular size form under specific conditions. Water at temperatures above about 90 degrees Celsius, at appropriate pressure and alkalinity, in contact with rock. On Earth, this is what happens at hydrothermal vents. Molecular hydrogen detected during that deep 2015 pass. This was the finding that generated the most attention, and its significance requires a moment to explain. Hydrogen in the plume is difficult to produce by any process other than water reacting with rock at depth, a reaction called serpentinization, which occurs when seawater percolates into hot ultramafic rock. And hydrogen is not merely a signature, it is food. On Earth, entire microbial communities live on hydrogen, combining it with dissolved carbon dioxide to produce methane and extract energy in the process. The reaction is called methanogenesis, and it is one of the most ancient metabolisms known. Organic molecules, simple ones first, methane, propane, formaldehyde. Then in 2018, complex organics, large macromolecular fragments with masses above 200 atomic units containing carbon rings and chains. In 2019 and afterward, nitrogen and oxygen-bearing organics of the kind that on Earth participate in amino acid chemistry. Phosphorus identified in 2023 in E-ring grains at concentrations far exceeding Earth's oceans. Phosphorus is one of the 6 elements essential to all known life and had been the conspicuous gap in the inventory. Its presence closed that gap. Assembled together, the picture is of a global subsurface ocean, confirmed as global rather than regional by measuring how Enceladus wobbles as it orbits, which showed the shell must be fully decoupled from the interior. The ocean is perhaps 10 kilometers thick beneath an ice shell that varies from around 20 kilometers at the equator to as little as 1 to 5 kilometers at the South Pole, where the plumes emerge. It is salty, it is in contact with rock. There is strong evidence that the contact is hot, and it contains carbon, hydrogen, nitrogen, oxygen, and phosphorus. That inventory has led some researchers to describe Enceladus as having every ingredient currently considered necessary for life, which is accurate and which is also where care becomes essential. Because organic molecules are not life, and the distinction is not a technicality. The word organic in chemistry means only that a molecule contains carbon, usually bonded to hydrogen. It carries no implication about origin. Organic molecules form abundantly through processes with no biological involvement whatsoever in interstellar clouds, on comets, in the atmospheres of giant planets, in laboratory flasks containing nothing but simple gases and an energy source. Meteorites that fell to Earth carry amino acids that formed in space before this planet existed. Life is built from organic molecules. It does not follow that organic molecules imply life, any more than finding bricks implies a house. The same caution applies to hydrogen and to hydrothermal chemistry. Serpentinization is a geological reaction. It produces hydrogen on worlds with and without biology, and it has been running on Enceladus regardless of whether anything is there to consume the product. What the hydrogen establishes is that an energy source exists, that if something were living down there, it would have something to eat. That is a statement about the environment, not about its occupants. And there is an argument that runs the other way, which deserves mention for honesty's sake. The hydrogen is escaping into space. If a substantial microbial population existed and were consuming hydrogen efficiently, less of it should be living. The observed abundance is not evidence of life. If anything, it is mildly consistent with nothing eating it. So Enceladus sits in a peculiar position. It is the most thoroughly sampled ocean beyond Earth, and everything sampled has been encouraging. Yet nothing found so far constitutes evidence of biology, and the people closest to the data are the most insistent on that point. What Enceladus has actually delivered is a complete list of ingredients, water, energy, and the chemical elements in a place where they can be measured directly. Which raises the question that has to be answered before any of it means anything. What does an ocean actually need in order to support life? Not in principle, but in practice, measured against the only examples we have ever been able to study. And the most instructive of those examples are found in the darkest places on our own planet. In February of 1977, a small submersible descended 2.5 kilometers into the Pacific Ocean, north of the Galapagos Islands. The team aboard were geologists. They had come to look at rocks, specifically, to investigate anomalous temperature readings near a spreading ridge on the seafloor, where new crust is created as tectonic plates pull apart. They expected to find warm water venting through fresh basalt. That was the entire scientific objective. What they found instead was an ecosystem. Around the vents, in complete darkness at pressures approaching 250 atmospheres, the seafloor was crowded with animals. Clams the size of dinner plates, white crabs, mussels in dense beds, and most extraordinarily tube worms meters long, anchored in clusters, with soft red plumes extending from white sheaths into the shimmering water. The submersible carried no biologist. There had been no reason to bring one. Nothing in the accepted understanding of the deep ocean predicted this. Below about 200 meters, sunlight becomes too faint for photosynthesis. Below 1,000, there is no light at all. The deep seafloor was understood to be a food desert, a place where life persisted only sparsely, subsisting on the slow drizzle of organic debris sinking from the sunlit layers far above. Marine snow. Whatever fell. A dense, thriving community at that depth had no explanation. Something was supplying energy locally, and it was not the sun. The answer turned out to be chemistry. Water percolating down through cracks in the fresh volcanic rock near a spreading ridge is heated enormously, reaching temperatures well above the normal boiling point, kept liquid only by the crushing pressure. On its way through, it reacts with the surrounding rock, stripping out dissolved compounds. When it returns to the seafloor and meets cold, oxygen-bearing seawater, it emerges carrying a load of chemicals that are, in that context, extremely energetic. Hydrogen sulfide above all, along with hydrogen, methane, and dissolved metals. Hydrogen sulfide is toxic to most life on Earth. To certain bacteria and archaea, it is fuel. These organisms perform chemosynthesis. They oxidize hydrogen sulfide, capture the energy released, and use it to fix carbon dioxide into organic compounds, building sugars and cell material from scratch. It is the same net achievement as photosynthesis, producing food from inorganic ingredients, but the energy comes from a chemical reaction rather than from light. Those microbes are the base of the food web at the vents. The giant tube worms, which have no mouth, no gut, and no anus, house them internally by the billion in a specialized organ, supplying them with the sulfide and oxygen they need, and living on the organic compounds they produce in return. The clams and mussels host similar symbionts. The crabs and fish eat the animals that host them. An entire ecosystem, complete from primary production to predators, running with no input from the sun at all. The discovery reframed a question that had seemed settled. Sunlight was not a requirement for life. It was one energy source among at least two, and the second one is available in places sunlight never reaches. There's a further vent system worth mentioning, found in 2000 and called the Lost City, which sits not on a ridge axis but on older crust some kilometers away. Its chemistry is different and, for our purposes, more interesting. Rather than volcanic heat driving the system, the energy comes from serpentinization, the reaction between seawater and ultramafic rock, which releases heat directly and produces hydrogen and methane in abundance. Lost City's vents are cooler, longer-lived, highly alkaline, and they have been operating continuously for something like 120,000 years. Some researchers consider this class of environment the more plausible setting for the origin of life on Earth, precisely because it does not depend on volcanic activity and can persist for enormous spans of time. It is also the environment most directly analogous to what may exist on the seafloor of an icy moon. The broader lesson from Earth's biology is that the range of conditions life tolerates is far wider than anyone assumed a century ago. Organisms called extremophiles have been found essentially everywhere anyone has looked with sufficient care. Some live in near boiling water in hot springs, with proteins stable at temperatures that would cook an egg. Others thrive below the freezing point, in brine pockets within Antarctic sea ice or in permafrost, where cells have been revived after tens of thousands of years. There are organisms in acid mine drainage at a pH near zero, and others in soda lakes at the opposite extreme. There are microbes in salt-saturated brines where nothing else survives, and microbes in the deep biosphere, kilometers down inside solid rock, feeding on hydrogen produced by radioactive decay, splitting water molecules, dividing perhaps once a century. Pressure appears to be barely a constraint at all. Microbial life is found at the bottom of the deepest ocean trenches, at over 1,000 atmospheres, and pressure-adapted organisms function at levels well beyond that. Radiation likewise. One bacterium is known to survive doses thousands of times what would kill a human, by repairing its shattered chromosome within hours. The recurring theme is that life adapts to almost anything except the absence of liquid water. Deprive an environment of water and biology stops. Provide water and an energy source, and organisms are usually found. Which allows a reasonably specific list of what a subsurface ocean would need. Liquid water sustained over long periods rather than briefly. The essential elements carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, all are common in the material that formed the outer solar system. An energy source which in a lightless ocean means chemical disequilibrium, two substances present together that would react and release energy, kept apart or continuously replenished. Hydrogen and carbon dioxide, sulfide and oxygen, any pairing where the reaction has not yet run to completion. A stable environment, since the chemistry that becomes biology takes time and is easily disrupted. And time itself, on Earth, the interval between the planet becoming habitable and the earliest reasonably confident traces of life, is a few 100 million years, possibly less. That is the only data point we have for how long the process takes, and a single data point supports no generalization at all. Now hold that list against what has been established about these moons, and a distinction becomes unavoidable. Every item on that list describes an environment, not one of them describes an organism. Habitable does not mean inhabited. This is the most important sentence in the entire subject, and it is also the one most consistently lost in the retelling. A habitable environment is a place where life could survive if it were present. Whether life is present is a completely separate question, and no amount of environmental characterization can answer it. The reason the distinction matters is that we have no idea how difficult the origin of life actually is. We know it happened once here. We do not know whether it happens readily wherever conditions permit, or whether it required some extraordinarily improbable sequence of events that might not repeat in 100 billion suitable worlds. Both possibilities are entirely consistent with the single example available. Which means that finding water, chemistry, and energy on another world establishes exactly one thing, that the question is worth asking there. It does not tilt the answer. There are deserts on Earth so dry that soil samples come back sterile, habitable by every measure except water availability, and empty. There are sealed subsurface environments that appear suitable and contain nothing. Habitability is a necessary condition, not a sufficient one, and the gap between the two is where all the uncertainty lives. Still, the necessary conditions have to be identified before anything else can proceed. And what makes this particular story unusual is how many places seem to satisfy them. Because Europa and Enceladus are not the only worlds where an ocean may be hiding. Within Jupiter's own system, orbiting further out, there is a moon so large it would be counted a planet if it circled the sun, and inside it, the evidence points to something considerably stranger than a simple sea beneath ice. There is a moon in this solar system, larger than the planet Mercury. Ganymede is 5,268 kilometers across, bigger than Mercury by a comfortable margin, and about 3/4 the diameter of Mars. It is the largest moon anywhere around any planet, and if it orbited the Sun independently rather than Jupiter, the question of whether to call it a planet would never have arisen. Its mass tells a different story than its size. Despite being larger than Mercury, Ganymede is only about half as massive because it is not a rocky body. It is roughly equal parts rock and water ice by mass, which makes it far less dense than any of the inner planets. Its surface gravity is about 1/7 of Earth's, similar to our moons, despite Ganymede being substantially bigger. It orbits Jupiter at a little over 1,000,000 kilometers, taking just over 7 days to complete a circuit, and like its siblings, it keeps one face permanently turned toward the planet. The surface divides cleanly into two kinds of terrain, and the division is visible even in modest telescopes as a modeling of light and dark. About 1/3 of the surface is dark, heavily cratered and ancient, the oldest terrain on the moon, dating back perhaps 4 billion years. These regions are informally called regions, and they carry the full record of early bombardment. The remaining 2/3 is brighter, younger, and grooved. This terrain is covered in extensive systems of parallel ridges and troughs, sometimes running for thousands of kilometers, cutting across each other in complex patterns. The grooves are tectonic, the result of the crust being stretched and faulted, probably during a period of internal reorganization several billion years ago. Whatever caused it has since stopped. Ganymede's surface is not being resurfaced now. The grooved terrain is old, just less old than the dark regions. So on the face of it, Ganymede looks like a world that was once active and has since gone quiet. The interior tells a different story, and the first indication came from an instrument reading nobody expected. In 1996, the Galileo spacecraft made a close pass and detected that Ganymede has its own magnetic field. Not an induced one, a genuine intrinsic field, generated internally with its own north and south poles. This is unique, no other moon in the solar system has one. Producing a planetary magnetic field requires a dynamo, a layer of electrically conducting fluid in motion deep inside the body. On Earth, it is liquid iron in the outer core, churning as heat escapes. For Ganymede to have a field, it must have a molten iron core that is still convecting today. The consequence is visible from Earth. Ganymede's field carves out a small magnetic bubble inside Jupiter's vastly larger one, a magnetosphere within a magnetosphere, and charged particles funneled along the field lines strike the moon's thin oxygen atmosphere near the poles, producing auroras. Ganymede has northern and southern lights. Those auroras became the tool for finding the ocean, in one of the more elegant pieces of remote sensing in planetary science. The reasoning, developed by a team using the Hubble Space Telescope in 2015, works like this. Ganymede's auroral belts are anchored to its own magnetic field, but Jupiter's field is also present, and it sweeps back and forth as the planet rotates. That changing external field should cause Ganymede's auroral belts to rock back and forth in response, like a compass needle disturbed by a moving magnet. How far they rock depends on what is inside the moon. If Ganymede's interior is solid, the belts should swing by about 6 degrees. But if there is a conducting salty ocean beneath the ice, that ocean generates its own induced field opposing the change, damping the motion considerably, reducing the swing to around 2 degrees. Hubble observed the auroras over several years and measured the rocking. It was about 2 degrees. The ocean was detected by watching lights in the sky shift by 4 degrees less than they otherwise would have. Independent support came from Galileo's magnetometer data, which showed an induced field component consistent with a conducting layer, and from gravity measurements constraining how mass is distributed inside. But Ganymede's interior appears to be considerably more complicated than Europa's, and this is where it becomes genuinely strange. Europa's water layer is around 100 kilometers thick. Ganymede's is closer to 800, an enormous quantity, far more than Europa or Earth. And at those depths, the pressure at the bottom of the water layer becomes extreme. Under high pressure, water ice does not stay as the familiar form we know. It transforms into other crystal structures, denser phases, packed more tightly, which are heavier than liquid water rather than lighter. These are labeled by Roman numerals, ice III, ice V, ice VI, and beyond. They form at pressures found deep inside large icy bodies and nowhere naturally on Earth's surface. Which means Ganymede's water layer may be stratified, ordinary ice on top forming the crust, beneath it, liquid ocean. Beneath that, a layer of high-pressure ice sitting on the seafloor because it is denser than the water above it. Some models go further and propose alternating layers, up to 3 separate liquid oceans sandwiched between ice layers of different phases, stacked like a club sandwich, each ocean sealed from the ones above and below. This arises because the freezing behavior of salty water changes with pressure in a way that can produce multiple stable liquid zones at different depths. Whether the layering is that elaborate remains genuinely uncertain, and simpler 2-layer models remain viable. But the possibility carries a significant implication for habitability, and it is not a favorable one. Europa's ocean, as far as anyone can tell, sits directly on rock. Water in contact with a rocky seafloor is where the interesting chemistry happens, where minerals dissolve, where serpentinization can occur, where hydrothermal systems can form. That contact is the engine. On Ganymede, if a thick layer of high-pressure ice separates the ocean from the rocky interior, then that contact may not exist at all. The ocean would be sealed between ice above and ice below, isolated from the mineral chemistry that makes an ocean nutritionally interesting. Some researchers argue the barrier is not absolute, that material can transfer through high-pressure ice over long timescales, or that the ice at the boundary is warm enough to permit some exchange. Others suggest the deepest ocean layer might still touch rock in places. The question is unresolved, and it is one of the main things a future mission would aim to constrain. So Ganymede's status is peculiar. It almost certainly has the largest subsurface ocean of any body we know, possibly containing more water than all 4 of the moons we are considering combined. It has a molten core, an intrinsic magnetic field, and a magnetosphere that partially shields its surface from Jupiter's radiation, which is itself a point in its favor for habitability. And yet its ocean may be the least promising of the group, because it may be the most thoroughly sealed. A spacecraft is on its way to find out. The European Space Agency's JUICE mission launched in 2023 and will arrive in the Jovian system in the mid-2030s, eventually entering orbit around Ganymede, the first spacecraft ever to orbit a moon other than our own. It carries an ice-penetrating radar designed to measure the shell's thickness directly, along with instruments to map the magnetic field and gravitational structure in detail. What Ganymede has already established, though, does not depend on that mission. 2 moons of Jupiter formed from the same material at the same time, both hiding oceans. A moon of Saturn, a 10th their size, doing the same. Whatever produces subsurface oceans is not a peculiarity of one unusual world. It appears to be something that happens routinely, wherever the conditions allow. Which raises an obvious follow-up. If it happens routinely, how far does it extend? Europa is close to Jupiter and violently flexed. Ganymede is further out. What about a moon further still, one so distant from the planet that the forces which power the others have faded almost to nothing, and whose surface has not changed in 4 billion years? There is a surface in this solar system that has been left alone since the beginning. Callisto's face is the oldest landscape known, a crust that has recorded impacts continuously for 4.5 billion years and erased none of them. It is saturated. Every part of it is covered in craters, and new craters can only form by destroying older ones because there is no empty ground left anywhere. This is what a truly dead world looks like. Nothing has resurfaced it, nothing has fractured it, nothing has flowed across it. Whatever happened to Callisto happened when the solar system was young, and since then it has simply sat there, accumulating scars. Which makes it the most unlikely place in this entire story to find an ocean. Callisto is the outermost of Jupiter's 4 large moons, orbiting at nearly 1,900,000 kilometers, almost 3 times Europa's distance, and taking 16.5 days to complete a circuit. It is very nearly the same size as Mercury, at 4,820 kilometers across, making it the 3rd largest moon in the solar system. Its density is low, around 1 8/10 grams per cubic centimeter, which indicates a composition of roughly equal parts rock and ice. And here the first oddity appears. Callisto appears to be only partially differentiated. Differentiation is the process by which a body separates into layers, with dense material sinking to the center and lighter material rising. Earth is fully differentiated: iron core, rocky mantle, thin crust. Europa and Ganymede are differentiated too. Callisto seems not to be. The gravity measurements suggest its interior is a mixture of rock and ice that has never fully separated, becoming denser gradually with depth rather than forming distinct layers. That is informative because differentiation requires heat. A body that separates into layers must have been warm enough for material to move and sort itself. Callisto's incomplete differentiation means it never got hot enough to finish the process. It formed slowly, accreted gently, and has been losing heat ever since without ever having much to lose. Which is exactly why an ocean there is so surprising. The evidence comes from the same magnetic technique that revealed Europa's ocean. Galileo made several close passes of Callisto, and its magnetometer detected an induced magnetic field, a signature responding to Jupiter's rotating field, opposing the changes in the manner of a conducting layer within the moon. The measurement was clear enough to be taken seriously. The interpretation is a salty liquid layer, probably beginning somewhere between 100 and 200 kilometers below the surface and possibly tens of kilometers thick. But the evidence for Callisto is genuinely weaker than for the others, and it is worth being precise about why. For Europa, the magnetic signature is strong and has been confirmed across multiple flybys with consistent results, and it is supported by an entire body of surface geology that independently demands a subsurface liquid layer. 2 lines of evidence pointing the same way. For Enceladus, the material is being ejected into space and has been sampled directly. There is no interpretation involved. For Ganymede, the magnetic evidence is reinforced by the auroral measurement, which was an independent method with an independent instrument reaching the same conclusion. For Callisto, there is essentially 1 line of evidence, the induced field, and no supporting geology whatsoever. The surface offers no cracks, no chaos terrain, no resurfacing, nothing that would independently suggest liquid below. There are also alternative explanations for the magnetic signal that have not been fully excluded. Callisto has a thin ionosphere, and a conducting ionospheric layer could in principle contribute to the observed field. The measurements were taken during a limited number of passes under a limited range of conditions. And some analyses have suggested the induced signature is best fit by a very thin conducting layer at a particular depth, which is a more delicate conclusion than a thick global ocean. Recent modeling has actually complicated the picture further, with some studies suggesting the ocean, if it exists, might be thinner and deeper than earlier estimates, perhaps only a few tens of kilometers, buried beneath a much thicker ice shell. So Callisto's ocean is a real possibility that remains genuinely uncertain, and that uncertainty is part of what makes it interesting rather than a flaw in the story. The obvious question is how it could be there at all. Callisto is too far from Jupiter for meaningful tidal heating. It sits outside the gravitational relationship that binds the 3 inner moons together, and its orbit is nearly circular, which means very little flexing occurs. Whatever keeps its interior warm cannot be the mechanism that operates on Europa. The answer is probably twofold. Radioactive decay in the rocky component provides a slow, steady trickle of heat that has never stopped. It is not much, but it has been running for 4.5 billion years, and a large body loses heat slowly. Callisto is big enough that its interior is meaningfully insulated by everything above it. And then there is chemistry. Ammonia, if present in the water, and there is reason to expect it in bodies that formed in the outer Jovian system, dramatically lowers the freezing point. An ammonia-water mixture can remain liquid at temperatures well below zero, down toward 200 Kelvin in the right proportions. Dissolved salts contribute further. Combine marginal internal heat with an antifreeze, and a layer of liquid can persist where pure water would have frozen solid billions of years ago. If that is what has happened, then Callisto's ocean is a very different kind of place from Europa's. It would be cold, near its freezing point rather than comfortably above it. It would be laced with ammonia and salts. It would be sandwiched between ice above and at Callisto's size and water content, quite possibly high-pressure ice below, cutting it off from rock. And it would be extraordinarily quiet. No tidal churning, no hydrothermal activity, no exchange with a surface that has not moved in 4 billion years. An ocean, but a static one. Sealed, cold, chemically undisturbed, and undisturbed for essentially the entire history of the solar system. Whether such a place could support life is doubtful, and for a specific reason. Life needs energy, and energy in a lightless ocean comes from chemical disequilibrium, from reactions that have not yet run to completion. In a sealed system with nothing replenishing the reactants, those reactions eventually finish. The chemistry reaches equilibrium, and the energy is gone. Europa's ocean may be continuously supplied, oxidants delivered from above through the churning ice, reduced compounds from the rock below. Enceladus visibly exchanges material with space. Callisto, as far as anyone can tell, exchanges nothing with anything. And yet there is a version of this that is worth holding on to, because dismissing Callisto too quickly would be its own kind of error. We have been wrong before about which worlds are interesting. Enceladus was a small, bright moon nobody expected anything from until a spacecraft changed course and flew close enough to look. Pluto was assumed to be a dead relic until we photographed mountains on it. The pattern in planetary science has consistently been that quiet-looking worlds turn out to have more happening than predicted, not less. Callisto has one further distinction, and it is a practical one. Sitting outside the harshest part of Jupiter's radiation belts, it receives a small fraction of the radiation that bombards Europa. Long-duration missions and even human presence are far more feasible there than anywhere else in the Jovian system, and it has been studied seriously as a potential base for exploration of the outer solar system. So 4 moons and the same possibility beneath all of them, 2 where the evidence is overwhelming, 1 where it is strong but the ocean may be sealed away, and 1 where an ancient, undisturbed world may be quietly holding liquid water beneath a face that has not changed since before the Earth had continents. Which leaves the question that connects them, and it is a physical one rather than a biological one. These moons sit 5 to 10 times further from the sun than we do, receiving a few percent of the sunlight that falls on Earth. Their surfaces are cold enough to be structural material. Something has been keeping them warm inside for 4.5 billion years, and on the moons closest to their giant planets, that something is powerful enough to have melted a world. Take a paperclip and bend it back and forth. After a dozen cycles touch the bend, it is warm. Nothing was added, no flame, no friction against another object, no electricity. The metal simply resisted being deformed, and that resistance converted the work of your fingers into heat inside the material itself. That is the entire mechanism. Everything that follows is the same process, scaled up until it can melt a world. Start with the force involved. Gravity weakens with distance. This is the crucial fact, and it is the reason tides exist at all. Jupiter pulls on Europa, but it pulls on the near side of Europa slightly harder than on the far side because the near side is closer. The difference is small in proportional terms. Across a body 3,000 kilometers wide, at a distance of 670,000 kilometers, the variation in Jupiter's pull is a fraction of a percent. But a fraction of a percent of Jupiter's gravity is still enormous. Jupiter has more than 300 times Earth's mass, and Europa sits closer to it than our moon does to us. The effect of that differential is to stretch. The near side is pulled toward Jupiter more strongly than the moon's center, and the moon's center more strongly than the far side, so the whole body is drawn out slightly along the line connecting it to the planet. Europa is not a sphere. It is a very slightly elongated ellipsoid, with its long axis pointing permanently at Jupiter. If that were the end of it, nothing would happen. A body held in a constant shape generates no heat. It would simply be a slightly oval moon, permanently deformed and entirely cold. The heat comes from the shape changing. Europa's orbit is not perfectly circular. Its eccentricity is small, under 1%, but it is not zero, which means the distance to Jupiter varies over each 3.5-day circuit. Closer means stronger tidal stretching, farther means weaker, so the elongation grows and shrinks continuously, twice per orbit. There's a second effect layered on top. Because the orbital speed varies while the rotation rate stays constant, the direction from Europa's center to Jupiter wobbles slightly back and forth as seen from the moon's surface, an effect called libration. So the tidal bulge does not simply grow and shrink in place. It also sweeps back and forth across the moon, dragging the deformation around the body. The result is that the entire moon is being kneaded, stretched, released, and rocked on a 3.5-day cycle without interruption for 4.5 billion years. The vertical movement of the surface has been estimated at tens of meters over each orbit. Europa's ice rises and falls like an enormous slow tide, except that the ice itself is what is rising. And every cycle of that deformation dissipates energy as heat, distributed through the interior, concentrated wherever the material deforms most readily. The ice shell absorbs some, the rocky interior absorbs some. If a liquid ocean exists, the boundary layers where solid meets liquid absorb a great deal. Now the question that makes this whole subject work: why does Europa's orbit stay eccentric? It should not. Tidal dissipation is a damping process. The energy being converted into heat comes from somewhere, and it comes from the orbit itself, from the eccentricity. Left alone, tidal heating circularizes an orbit and then shuts itself off. The moon settles into a perfect circle, the flexing stops, the heating ends, and the interior freezes. On any reasonable timescale, Europa's orbit should have circularized long ago, and its ocean should be solid ice. The reason it has not is one of the most elegant arrangements in the solar system, and it involves 3 moons rather than 1. Io, Europa, and Ganymede are locked in a resonance. For every single orbit Ganymede completes, Europa completes exactly 2, and Io exactly 4. The ratio is precise, 1 to 2 to 4, and it is enforced by gravity. What this means physically is that the moons meet each other in the same configurations repeatedly. Io and Europa pass one another at the same point every time. Europa and Ganymede do the same. Because the alignments repeat rather than being scattered randomly around the orbits, the small gravitational tugs the moons exert on each other accumulate in the same direction each time, instead of averaging out to nothing. Those repeated tugs pull each moon slightly off a circular path continuously. The resonance pumps eccentricity into the orbits at roughly the rate tidal dissipation removes it. This is called the Laplace resonance, after the mathematician who described it, and it is the reason there is an ocean under Europa's ice. Without it, the flexing would have stopped billions of years ago. The same arrangement produces a far more dramatic result on Io, which sits closest to Jupiter and is flexed hardest. Io has no water left, but it has the most intense volcanism in the solar system, hundreds of active volcanoes, some throwing plumes hundreds of kilometers into space, a surface completely repaved by lava. That is tidal heating with the dial turned up, and it is a useful reminder that the process is not gentle. Ganymede sits at the outer end of the resonance chain and receives the weakest forcing of the three. Its present-day tidal heating is modest. But its orbital history was probably more eventful than its current state suggests. Models indicate the moons migrated into the resonance over time, and Ganymede may have passed through a phase of much higher eccentricity in the past, generating far more heat than it does now. That episode is one leading explanation for the grooved terrain, a period of internal reorganization driven by heating that reshaped the crust and then ended. Which explains why Ganymede looks like a world that was once active and stopped. Callisto is outside the resonance entirely. Nothing maintains its eccentricity, its orbit is nearly circular, and its tidal heating is negligible. Whatever liquid it retains is kept warm by radioactive decay and antifreeze chemistry, not by Jupiter. Enceladus tells a similar story around Saturn, with one variation that has caused persistent difficulty. Enceladus is in a 2-to-1 resonance with Dione, a larger moon further out. Enceladus completes 2 orbits for every one of Dione's, and that arrangement maintains the eccentricity that drives the flexing. The problem is arithmetic. Enceladus is tiny, a tenth of Europa's diameter, and calculations of how much heat the resonance should generate have consistently fallen short of the heat actually observed pouring out of the South Polar region. The measured output is several times what standard models predict. Several explanations have been proposed. The dissipation may be concentrated in a particular way at the boundary between the ocean and the rocky core, where a porous, water-saturated interior could absorb far more energy than solid rock. Or the activity may be episodic, Enceladus cycling between periods of intense heating and long dormancy, and we happen to be watching during an active phase. The question is not settled, which is itself worth noting. The mechanism is established, the accounting is not. Step back and the significance becomes clear. For most of the history of astronomy, there was one source of planetary warmth, and it was the sun. Distance from a star determined temperature, temperature determined whether water could be liquid, and that determined where life could exist. It was a simple rule, and it produced a narrow habitable zone, a thin ring around each star, and nothing worth considering beyond it. Tidal heating breaks that rule completely. It supplies energy that has nothing to do with sunlight, drawn instead from orbital mechanics, from the angular momentum of a moon's motion around its planet, converted into heat through the friction of endless deformation. And it works anywhere. Any icy body, orbiting any sufficiently massive planet, held in an eccentric orbit by a resonance with its neighbors, can melt from within regardless of how far it sits from any star. The solar system contains 4 giant planets with dozens of moons between them. Other stars have giant planets too, and no reason to lack moons. Which means the number of places where liquid water might exist is not the small number implied by habitable zones. It may be very much larger. So the ingredients have assembled themselves, water in quantities exceeding Earth's, the chemical elements sampled directly in a plume, energy from gravity rather than light, and time 4.5 billion years of it uninterrupted. That is the full list, every condition currently thought necessary, met in at least one place we can point to. Which returns us to the question that has been waiting since the beginning, and it can no longer be deferred. Descend into Europa's ocean and there is nothing to see, not dimness, absence. No light has reached that water in 4.5 billion years. There is no surface. Look up and there is only the underside of the ice, extending in every direction to a horizon that does not exist because the ice does not end anywhere. There is no shore, no island, no break. The entire world is roofed. The water is cold, near freezing, and salty. The pressure at the bottom, under 100 kilometers of ocean plus the ice above it, is greater than at the deepest point in any terrestrial trench, but the low gravity moderates it, and it is not beyond what life on Earth already tolerates. And down there at the base of all that water there is rock, a seafloor unseen in permanent darkness, possibly warm. So could something be alive there? The honest structure of the answer is that it splits into two questions that get conflated constantly, and separating them is the only way to think about it clearly. The first is whether the environment could support life. That question is about physics and chemistry, and we can make real progress on it. The second is whether life ever began there. That question is about a process we do not understand, having observed it exactly once, and we can make almost no progress on it at all. Start with what can be assessed. Habitability, as the term is actually used by scientists, means something narrower than the everyday sense. It does not mean pleasant or Earth-like or suitable for us. It means an environment where known biochemistry could function and persist. Liquid water, the necessary elements, a source of usable energy, and conditions stable enough for long enough. By that standard, Europa's ocean looks genuinely promising, and the reason is the seafloor. An ocean sitting on rock is a chemically active system. Water reacts with minerals. Dissolved compounds are released. If any part of that seafloor is warm, and the tidal heating that keeps the ocean liquid must also be heating the rocky interior, then hydrothermal circulation becomes plausible, with water percolating into hot rock, reacting and returning enriched. The specific reaction that matters most is serpentinization, where water meets iron and magnesium-rich rock and produces hydrogen as a byproduct. Hydrogen is one of the most useful energy sources in biology. On Earth, entire communities live on it. That supplies one half of what an organism needs. Energy comes from reactions, and reactions need two participants, something to give electrons and something to take them. Hydrogen gives, something has to take. Which is where Europa's surface becomes relevant in a way that would not be obvious. Jupiter's radiation environment is brutal. Charged particles trapped in the planet's magnetic field bombard Europa continuously, and when they strike water ice, they break it apart, producing oxygen, hydrogen peroxide, and other oxidizing compounds. These accumulate in the surface ice. If surface material cycles downward, carried into the shell by the churning that produces chaos terrain, or drawn down where the crust converges, then oxidants would be delivered into the ocean. Oxidants from above meeting hydrogen from below, a chemical gradient running through the ocean, continuously replenished from both ends. That is precisely the arrangement that powers life in Earth's dark places, and it would make Europa's ocean an energetically open system rather than a sealed one running down toward equilibrium. Whether it actually happens depends on the ice shell's thickness and how vigorously it recycles, which nobody knows. Enceladus presents a different profile. Its ocean is far smaller, but the evidence for seafloor activity is more direct. The silica nanograins, the hydrogen, the salts all point to hot water contacting rock right now. And the plumes demonstrate that the system is not sealed. Material moves. The concerns with Enceladus are size and time. A small ocean has less of everything, and the question of whether the activity has been continuous for billions of years or is a recent episode remains open. If the moon has cycled between active and dormant phases, the ocean may not have had the uninterrupted stretch that chemistry may require. Ganymede has the largest ocean of any of them, and possibly the least accessible chemistry, if high-pressure ice separates the water from rock. An ocean sealed between two ice layers has no mineral supply and no obvious energy input. Callisto is the least promising, for reasons already established. A cold, probably static ocean with no evident exchange of anything with anywhere. So the ranking that emerges is not about which ocean is largest. Europa and Enceladus lie not because they hold the most water, but because they are the two where something appears to be moving material around. Now the harder question, and here the honesty has to be complete. There is no evidence of life on any of these worlds, none. Nothing detected on Europa, Enceladus, Ganymede, or Callisto constitutes a biosignature. Every observation made so far is fully explained by chemistry and geology, operating without any biological involvement whatsoever. That is not a hedge or a formality. It is the actual state of knowledge, and the researchers closest to the data state it more firmly than anyone. What we have found is a set of environments where the question is not absurd. That is genuinely new. A generation ago, there was nowhere beyond Earth that could be discussed this way, but it is a statement about the questions worth asking, not about the answers. And there is a deeper uncertainty underneath, which is easy to skip past and shouldn't be. We do not know how life begins. Not in outline, not in mechanism, not in probability. We know it happened on Earth early, within a few 100 million years of the planet becoming habitable, perhaps sooner. We know the chemistry that must have been involved in broad terms. We do not know the sequence of steps, and we have never made it happen in a laboratory despite 70 years of trying. Which means we cannot say whether the origin of life is easy or nearly impossible. Both possibilities fit the single data point we have. If it is easy, if any environment with water, energy, and carbon chemistry will produce life given a few 100 million years, then these oceans are probably inhabited, all of them. If it required an extraordinarily improbable sequence of coincidences, then Earth may be the only place in the galaxy where it happened, and every one of those oceans is sterile. Nothing currently known distinguishes between these scenarios. One example tells you that something is possible. It tells you nothing about how often it occurs. There's a version of this argument that gets made in the other direction, that life appeared on Earth so rapidly after conditions permitted that the process must be easy. It is a reasonable intuition, and it does not survive scrutiny, because we could only be here to make the observation on a planet where life did arise early enough for us to evolve. The sample is filtered by the fact that we exist in it. So the situation is this: 4 moons with hidden oceans, 2 with strong evidence of the chemistry and energy that biology would require, 0 evidence of biology, and a fundamental question about how difficult the origin of life is, to which nobody has any answer at all. If anything is down there, the realistic expectation is microbial, not because complexity is impossible, but because complex life on Earth took billions of years and required, among other things, an enormous accumulation of atmospheric oxygen that photosynthesis produced, and a lightless ocean has no obvious route to. Single-celled organisms, sparse, slow metabolizing, clustered wherever the chemistry is richest, probably near the seafloor, if anywhere. Even that would be the most significant discovery in the history of science, and the reason is worth stating precisely. It would not simply mean that life exists somewhere else. It would mean that life began twice independently in the same solar system. And if it began twice in one ordinary planetary system, then the process cannot be rare, and the number of inhabited worlds in a galaxy of hundreds of billions of stars would be enormous. A single microbe under Europa's ice would change our estimate of how much life exists in the universe by many orders of magnitude in a single measurement. Which is why the question will not be left alone, and why it is not going to be answered by argument. At some point, someone has to go and look, and that turns out to be extraordinarily difficult, because the thing we want to sample is sealed beneath kilometers of ice, on a world 500 million kilometers away, bathed in radiation intense enough to destroy electronics in a matter of weeks. Consider the practical problem for a moment, because it is worse than it first appears. To sample Europa's ocean directly, a spacecraft would have to land safely on an unmapped surface of fractured ice, then melt or drill through something between 15 and 30 kilometers of it, a depth greater than the deepest hole ever bored into Earth, while operating autonomously, powered by whatever it brought with it, in an environment where Jupiter's radiation delivers a lethal dose to electronics within weeks. Nobody knows how to do this. Concepts exist, but no agency has a funded plan, and the engineering gap is not small. So the search proceeds differently, not by reaching the ocean, but by reading what the ocean leaves behind. The first serious attempt is already underway. Europa Clipper launched in October of 2024 and will arrive in the Jovian system in 2030. It is the largest planetary spacecraft NASA has ever built. Its solar arrays span more than 30 meters, necessary because sunlight at Jupiter is a 25th of what falls on Earth. Its design reflects the radiation problem directly. Rather than orbiting Europa, where it would be inside the worst of Jupiter's radiation belts continuously and would fail within months, Clipper orbits Jupiter instead, on a long looping path that sweeps past Europa on close approaches, and then retreats to safer distances to recover and transmit data. Roughly 50 flybys are planned, some as low as 25 kilometers above the surface. The electronics sit inside a thick aluminum zinc vault at the spacecraft's center. The instruments are chosen to answer specific questions. An ice-penetrating radar will look through the shell itself, sending radio waves down and listening for reflections from internal layers and, ideally, from the ice-water boundary. If it works, it will measure the shell's thickness directly, settling a debate that has run for 25 years, and that determines nearly everything about whether the ocean can exchange material with the surface. A magnetometer will refine the induced field measurement, which constrains the ocean's depth, thickness, and salinity far more precisely than Galileo's limited passes allowed. Cameras and spectrometers will map the surface at high resolution and determine its composition, particularly the reddish material along the fractures, establishing whether it came from the ocean and what the ocean's chemistry is. Mass spectrometers and a dust analyzer will sample whatever tenuous material surrounds the moon, sputtered surface particles, any escaping gases, and, if they exist, plume material. That last possibility deserves care. Observations from Hubble and reanalysis of old Galileo data have produced several tentative detections of water vapor plumes near Europa's south pole. Some were reasonably convincing, others could not be reproduced. If plumes exist, they appear to be intermittent and far weaker than Enceladus's, and their existence remains genuinely unconfirmed. Clipper will look, but nobody is counting on it. Notably, Clipper is not a life detection mission. It carries no instrument designed to find organisms. Its stated goal is to determine whether Europa is habitable, to characterize the ocean, the shell, the chemistry, and the energy sources. Whether anything lives there is explicitly a question for later. The European Space Agency's JUICE mission, launched in 2023, will study Ganymede, Callisto, and Europa on a different schedule, eventually settling into orbit around Ganymede in 2034, the first spacecraft ever to orbit another planet's moon. Enceladus presents an entirely different opportunity, and it is the reason many researchers consider it the better target despite its small size. The ocean samples itself. A spacecraft does not need to land, drill, or melt anything. It needs to fly through a plume. Cassini did this repeatedly, but Cassini was not built for it. Its instruments were designed in the 1980s, before anyone knew Enceladus had plumes, and they were optimized for entirely different questions. The mass spectrometer had modest resolution by modern standards, and the encounters occurred at high velocity, around 30,000 kilometers per hour, fast enough that fragile molecules striking the detector would shatter on impact. Anything complex would have been broken before it could be measured. A purpose-built mission would fix both problems. Slower passes, achieved by entering orbit around Saturn or Enceladus itself, rather than making high-speed flybys. Instruments with far higher mass resolution, capable of distinguishing molecules that differ by fractions of an atomic mass unit. Gentle collection methods designed to capture particles intact. Several concepts have been developed. ESA has identified an Enceladus mission as a large-class priority for the 2040s. NASA's most recent planetary science decadal survey ranked an Enceladus orbiter and lander highly, and various proposals have circulated for missions that would orbit, sample repeatedly, and eventually land near the Tiger stripes to collect fresh fallout directly. None is currently funded and flying. The timelines involved run to the 2040s and beyond. Which raises the question that matters most. If such a mission flew through a plume, what would actually count as evidence? The answer is a hierarchy, and understanding it is the key to reading any future announcement sensibly. Liquid water is not evidence. It establishes only that the environment is not immediately disqualified. Organic molecules are not evidence. They form abundantly without biology throughout the solar system and in interstellar space. An energy source is not evidence. Hydrogen from serpentinization is a geological product. All three together are still not evidence. They describe a habitable environment, which is a statement about conditions. Where it starts to become interesting is with patterns, specifically with distributions that chemistry does not produce but biology does. The clearest example involves chirality. Many organic molecules come in two mirror image forms, like left and right hands. Ordinary chemical synthesis produces both in equal amounts because there is no reason to prefer one. Life on Earth uses almost exclusively one form: left-handed amino acids, right-handed sugars. A sample showing a strong excess of one hand over the other would be difficult to explain without biology, though not impossible. Another involves the distribution of carbon chain lengths. Life produces lipids with strong preferences for particular lengths and pronounced patterns favoring even or odd numbers of carbon atoms. Abiotic synthesis produces smooth distributions that decline gradually with increasing size. A spiky, structured pattern is a signature. A third involves isotopes. Biological processes discriminate slightly between isotopes of the same element. They preferentially use the lighter version because it reacts marginally faster. Carbon in living material on Earth is measurably depleted in carbon-13 relative to its surroundings. Sustained isotopic fractionation in a sample would be suggestive. A fourth involves complexity itself. Some researchers have proposed that molecules above a certain threshold of structural complexity cannot form in appreciable quantities except through a process that builds and copies them. That complexity beyond a limit is itself a signature, independent of what the molecule does. The strongest case would combine several of these independently. Not one anomaly, but chirality and chain-length patterns and isotopic depletion and complexity, all pointing the same direction in the same sample. Because the failure mode here is well documented, and it is the reason for the caution. False positives are the persistent hazard in this field, and the history is instructive. The Viking landers on Mars in 1976 carried biology experiments, and one returned a result consistent with metabolism. It has been debated for nearly 50 years, and the consensus explanation involves reactive chemistry in Martian soil rather than organisms. In 1996, a meteorite from Mars was announced as containing possible fossil microbes. The structures and chemistry were subsequently explained without biology. Detections of methane on Mars and phosphine on Venus have each generated intense interest, followed by prolonged disputes over whether the signal was even real. The pattern is consistent. Extraordinary claims arrive, non-biological explanations follow, and the community settles into ambiguity. Nobody wants to add another entry to that list. Which is why any serious life detection mission would be designed around ruling things out rather than confirming them. Carrying redundant instruments, measuring multiple independent signatures, and including controls to establish what the background chemistry produces on its own. And there is a further constraint that receives less attention but shapes everything: planetary protection. Any spacecraft sent to a potentially habitable ocean world must be sterilized to a demanding standard, because contaminating one of these oceans with terrestrial microbes would destroy the scientific value of the target permanently. Cassini was deliberately destroyed in Saturn's atmosphere in 2017, partly to eliminate any chance of it eventually striking Enceladus. Clipper is designed to avoid impacting Europa and will end its mission by crashing into Ganymede instead. So the realistic timeline runs like this. Through the 2030s, Clipper and JUICE will establish whether these oceans are habitable, how thick the ice is, what the water contains, whether material moves between the ocean and the surface. Sometime after that, if the answers are encouraging and the funding materializes, a mission designed specifically to look for life might fly. Anyone hoping for an answer soon should recalibrate. The people who will operate the first genuine life detection mission to an ocean world are, in many cases, not yet working in the field. Which leaves a question that does not require any of that hardware to consider, and which is, in the end, the more interesting one. What would it actually mean, either way? Stand on a shore at night and look out at dark water. You cannot see anything in it, but you know without needing to be told that it is full, that every liter contains millions of organisms, that the darkness below is dense with living things going about their business entirely without reference to you. That is the only ocean any human being has ever known. We have never encountered water and found it empty. Which may be the deepest source of our intuition about these moons, and it may be badly misleading. Earth's oceans are full because life arose here and had 4 billion years to spread into every available space. It says nothing about whether water elsewhere fills the same way. So consider both outcomes honestly, because both are genuinely possible, and one of them is usually treated as a disappointment when it should not be. Suppose we look thoroughly and find nothing. Suppose Europa Clipper maps the shell and confirms the ocean, and a later mission samples it, and a purpose-built spacecraft flies slowly through the plumes of Enceladus with instruments 100 times more capable than Cassini is, and every measurement comes back as chemistry. Organic molecules with smooth distributions, equal proportions of both mirror image forms. Isotopes exactly where geology predicts, no pattern anywhere that requires anything living. That result would not be a failure, it would be an answer, and a consequential one. It would tell us that habitability is not sufficient, that water, energy, carbon chemistry, and billions of years of stability can exist together without producing biology, which would mean the origin of life requires something beyond favorable conditions, something we have not identified and would then need to go looking for. It would also mean that Earth is far more unusual than we currently assume. If the only place biology arose is here, despite multiple suitable environments in this one ordinary planetary system, then the step from chemistry to life is a very high barrier indeed, and the universe may be largely empty of anything that could notice it. That is a lonelier conclusion. It is also an enormously important one, and it can only be reached by looking. And even setting the life question entirely aside, these worlds would have taught us a great deal. How ice shells behave over geological time, how oceans stay liquid without a star, how tidal energy moves through a body, how much water the solar system actually contains and where it went. What happens to chemistry when it is left alone in the cold for 4.5 billion years with nothing to consume it, a record that has been erased on Earth by the very biology we are trying to find elsewhere. Now suppose the other outcome. Suppose a mass spectrometer samples plume material and finds amino acids with a strong preference for one hand. Suppose the lipid distribution shows sharp structured peaks instead of a smooth decline. Suppose carbon isotopes come back depleted in the way biological carbon is depleted here, and suppose the results hold up under scrutiny by people determined to explain them away. Even if it is nothing but microbes, sparse, slow, clustered near a seafloor nobody will ever see, the consequence is difficult to overstate. Not because a microbe is impressive, because of what a second origin implies. Everything alive on Earth is related. Every organism ever studied shares the same genetic code, the same molecular machinery, the same fundamental architecture, which means all of it descends from a single ancestral population. Life on this planet is one event, one time, with 4 billion years of consequences. One event tells you nothing about frequency. It could have been inevitable, or it could have been a fluke of staggering improbability, and there is no way to distinguish these from inside a single example. Two events change that completely. If life arose independently on Europa or Enceladus in a different environment from different starting materials under different conditions, then the process cannot require any unrepeatable accident. It becomes something that happens when the conditions are right. And the conditions appear to be right in a great many places. There are 4 giant planets in this system alone, with dozens of moons. There is no reason to think other stars lack giant planets or that those planets lack moons. If subsurface oceans form routinely wherever an icy body is flexed by a massive neighbor, then the number of potentially habitable environments in the galaxy is not the modest count implied by habitable zones. It is orders of magnitude larger. A single microbe under Europa's ice would move our estimate of how much life exists in the universe by a factor nobody could confidently bound. There would be a scientific caveat worth keeping in mind even then. It would need to be established that the organisms represent a genuinely separate origin, that they are not related to Earth life, delivered long ago by material blasted off one world and landing on another, which is not impossible over billions of years. A discovery with unfamiliar biochemistry would settle it. Something suspiciously similar to terrestrial life would raise a difficult question instead. And one confirmed instance would still not mean life is everywhere. It would mean the barrier is lower than the pessimistic case allows. It would not tell us how much lower. Set both scenarios down side by side, though, and notice something about them. We do not know which one we are living in. Right now, at this moment, one of these is true. Either those oceans are inhabited or they are not, and the fact has been settled for billions of years, waiting, entirely indifferent to whether anyone ever finds out. That is an unusual position to be in. Most open questions in science are open because the answer is complicated. This one is open because nobody has been there. So return one last time to Europa. Picture the surface from above, white ice, brilliant in the faint sunlight, crossed by thousands of reddish fractures running in long curves across the whole globe. Blocks of crust tilted at odd angles where something below disturbed them. A landscape that has been rebuilt more recently than the dinosaurs died. Beneath it, 20 kilometers down, past the roof of ice that has no shore anywhere, an ocean twice the volume of Earth's, dark, salty, cold, and moving slowly under the pull of a planet 300 times the mass of our own. At the bottom, rock, possibly warm, possibly venting hydrogen into water that has been circulating over it since before this solar system had finished forming. And in that water, either something or nothing. We do not know. That is the honest end of it. Every piece of evidence assembled over the past 50 years has told us that the question is reasonable, and not one piece has told us the answer. There is something worth appreciating in that. We have spent most of our history assuming the important places in the solar system were the ones we could see, the surfaces, the landscapes, the things a telescope could resolve. It turns out that may have been exactly backward. The largest bodies of liquid water within reach are all invisible, sealed under ice, on worlds we dismissed as frozen and dead for 3.5 centuries. The most significant environments may be the ones with nothing to show from outside. So tonight, while everything here continues as it does, that water is still there, circulating slowly, dissolving minerals from rock it has never stopped touching. Warmed not by any star, but by the endless flexing of a moon that cannot escape its own orbit. It has been doing this since before there was anything on Earth to observe it, and it will continue long after. Perhaps empty. Perhaps holding something small and patient in the dark, which has been there all along, and which we have not yet learned how to read.